Okay, good morning, Physics 30. So this is kind of the way we're going to try and do this from the start. I'm going to send out these videos of me basically just going through our notes with me voice recorded over top. A couple things we're going to note. I'm going to try and use a stylus here as best I can to kind of start some things out. I have sort of kind of figured this out. I'm going to, if you see on the left-hand side, I'm kind of creating this dotted line that disappears. As I'm talking, I'm kind of just going to note about what I'm sort of talking about and where I am on the page as we go. You guys know my writing is pretty bad to begin with, but as you can see, this isn't actually the worst I've ever done, but it's hard for me to write small, so I'm going to try to be as exact as I can, and we'll see from there. So remember, if you see dots, that's just what I'm talking about at that current time. Okay. Also, I noticed that this thing really picks up my breathing, and it's kind of embarrassing, but I will just keep going, and you guys can kind of deal with it, I guess. Wish you guys were in the class. It'd be a lot easier to do this if you were, and yeah, it's kind of weird just sitting here talking to myself. So here we go, Chapter 12, Magnetics. Magnetics are cool because we've already talked about magnets lots, especially in earlier years, right? But we're going to get into this idea of how we're going to connect to Chapter 11 and electricity and Chapter 12 with magnets and kind of how they work together. All right, the first thing I usually show to introduce, and I want you guys to watch these videos. You can actually click these videos. If I turn my stylus off, you can actually click on these videos and it'll actually open them up even on your Google Chromebooks. You can watch these videos. They're called maglev trains. I really like them because they show kind of what we can do if we have the right technology here overall, right? So technology using electricity and magnetism, right? Using electricity and magnetism, we can create kind of this idea of better things and simpler things, and this kind of is more of a real world application, which I like. Try and watch all three. If you get a little bit too far into them or you get bored, that's fine to move on. You're not going to get tested on this kind of stuff. Alrighty. So our anticipation guide, you guys should have already done these questions. Please let me know if you're having any issues with these. You are going to need to rely on the textbook just a little bit more since you don't have this face-to-face contact with me. We are working on getting a once a week or twice a week. You guys can have a video chat with me if you're interested. We can kind of set up a Google Classroom sort of thing or Google Hangout and go from there. So, all right, so we're now looking at ferromagnetic rocks. They were kind of, the idea is that they found these rocks and they had magnetic properties, so they used them as magnets. Then William Gilbert decided he's going to investigate magnets, and he noticed that there's a few different things that don't work, right? For example, magnets don't work with their rub. They actually wrecks them if you rub them together. Versus electricity, if you rub two things together, you get this electrical effect. Okay, objects with an electrical charge can attract small objects like paper, right? We already know that from the previous chapter that electrical charge causes us to attract neutral objects, whereas magnetics really only going to attract magnetic objects, usually types of metal. Electrified objects attract from all sides, whereas magnets only attract from the poles. Magnets have a side. All right, so there's kind of this idea that they did not seem very similar, but over time we kind of learned a few things. All right, so the first couple things we learned are the three laws of magnets. One, there are two poles on any magnets, north and south. Opposite poles attract and like poles repel. We already know all this, right? But one thing to keep in mind is if I have a magnet that has a north and a south end, and I cut it in half, right? I chop it in half, I'm going to get two separate magnets, right? So do I have a magnet, one north and one south? And the answer is no. According to the rule number one, these two magnets will each have both a north and a south, and they'll be attracted together. Right, and that's kind of the whole concept of what it is. And if I cut this in half again, or if I cut this one in half, I'd get another two magnets, again, both with north and south on them. Right, so no matter how much you cut a magnet in half, if it's still magnetic, it has a north and a south pole. All right, and these two rules, you guys already know those two rules: opposites attract and likes repel. Okay. So as we go through here, we're going to see that we have our domain theory. Domain theory is pretty critical. If anything, you guys should probably put a little star here in your notes, right? That we have domain theory. Each electron spins its axis as it orbits the nucleus. This creates a mini magnetic field. Magnetic fields, electrons in a group of neighboring atoms can add together to act as a domain. Okay, so domain is like little mini magnetic fields or little mini magnets. All right, and most substances, right, when the reason they're not magnetic, so every object has this domain. Every object has a domain, right, and every atom and every particle creates a domain. Right, but on most substances, it looks like this. Their domains don't line up at all. They kind of cancel out. They cancel out, therefore they're not magnetic. Whereas on magnetic substances, they either naturally their domains align, or we can force their domains to align. Right, so there's lots of things that do that. Right, so I showed some of you guys those neodymium rings. Or magnets, sorry, not rings, and those have had their domains forced to align through a process where they melt them and then align them and then unmelt them and all that kind of stuff. And they end up staying like this. This here is a majority of objects. They're just not magnetic on their own. All right, this here is a video on how magnets work. This Minute Physics guy is really good. He's got a lot of stuff in there. I'll show you some videos, so check him out. He kind of shows how magnet works. All right. What we noticed is that when we had the north end of a compass, which way does it point? Well, it points north. If the north end of a compass points north, right? The north end of a compass points north, then the north pole is actually south magnetically. So north geographically, the north geographical pole is south magnetically. Okay, is south magnetically. So the north geographical pole is south magnetically, right? Because the north end of a compass, right? The north end of a compass points north, which means that the south end has to be at the top. Okay, and that's just an interesting thing, and it's something that you should know, is that magnetically, the North Pole is actually a south part of a magnet, right? There's a separation, so there's called geographic pole and magnetic pole, right? And so there's a separation where we have the geographic pole has to do with the axis of the Earth. The magnetic pole has to do with the magnetic field of the Earth. Those are two separate things, right? So we have the geographical pole axis, magnetic pole is magnetic field. Notice that we have south magnetic pole up here and north magnetic pole up here. We have north geographical pole and south geographical pole. Those are not the same thing. Pay attention to that, right? So we have there's a point here. If you're on the equator, right? If you're on the equator here, you wouldn't really notice a difference between these two things, right? You wouldn't really notice a difference between these two things. If you were up in this area, right? If you're between these two poles, at one point, if you keep walking, your compass will point this way. Your compass will point to the right there, but your understanding of geography would actually tell you that the North Pole is over here. So your compass would point at the south magnetic pole, but the North Pole would actually be here when you're in between those. It's not very far apart. If you want more information on that, again, watch Minute Physics here. Where is the true North Pole? There's a little bit of a separation there. Okay, so of course we have our magnetic force, which is an action and distance force. Anytime we have an action and distance force, we're going to have a field. Right? Magnetic field direction is defined as the direction of the north end of a compass needle points. The needle acts as a test object to test the direction of the field. Right? So what I've done here is I actually pre-wrote these in because I can't write that small very easily. It takes me a long time. So a gravitational field, we always just use a small mass. For an electric field, we used a proton, which direction a proton would go. And for magnetic field, we'd have whichever direction the north end of a compass points or the north end of a needle. Okay, so that kind of makes sense. And then if you look here, right, you're going to see that we have a iron filings around a magnet, and you can notice that these all point in the direction that they're supposed to, and it creates this kind of circular idea around the magnet, right? Okay, it looks going like this. All right, so we can also draw compass arrows, right? Compass arrows can tell us which direction it is going. So this is like our test object, right? So I have a magnet, looks like this. Well, it's obviously going to push the north needle, will go that way. On B here, the two norths will both repel the needle, so the needle will end up going at something like that, or that 45-degree angle. And for C, north will actually be attracted to the south, so it'll actually go in like so, okay? Electric fields, right? We know that we go out from positive to negative, right? Out from positive to negative, out from positive to negative. Magnetic fields, out from north to negative, out from north to negative, or to south, sorry, and out from north to south, right? So that's kind of the idea. Magnetic forces also do magnetic fields around a magnet. The results can be shown by using iron filings, right? So if I use iron filings, you get this pattern here, right? Do you see how the pattern there? That's if I was to use iron filings. If we do that and we draw it out, we get this magnetic field lines. All right, what I want you guys to notice is that in the center, in the actual bar here, there is some dotted lines in there. If you look inside the bar, there's some dotted lines. Okay, magnetic fields don't actually exist within the magnet themselves. The domains are already aligned and stuff like that. We can't use that. But where the solid lines are, that is actually everything. And that's where we're going to have magnetic fields show up. All right, so some practice problems here. Okay, sketch magnetic field lines caused by each of the following fields, right? So if I look here and I see that, I know I'm going to go out from north to south. Sorry, I'll use an actual pen here so you can actually see what I'm doing. So from north to south, again, north to south, north to south. If I have two norths, you look at the iron filings, or you look at that pattern, it's going to be the same as we would see with electric field with two protons, right? And they're going to kind of repel each other, and it's going to go away, okay? Horseshoe magnet, the top part is we always go out from north and to south, so that actually creates this kind of loop, right? And this loop gets kind of larger as we go, or smaller on the inside. Okay, in the center here is kind of a little bit harder to do because you have attraction from north to south and attraction from north to south, and it just gets very complex. We're going to deal mostly with the outside of a horseshoe magnet, and we have this nice north to south concept where it makes a little loop, and we have a very much more consistent magnetic field than we would if we had a bar magnet. All right. So the next thing we have is a magnet can be created from a coiled wire. Okay, these are called magnetic fields. All right, magnetic fields are pretty powerful. Holy man, they're called electromagnets. All right, electromagnets are very powerful. All right, this is what we use to kind of lift a car in a junkyard, right? If you've seen it on a movie, they lift the car up, right? They lift the car up, and then they move it somewhere, and then all of a sudden the magnet turns off and the car drops. Right, that is an electromagnet. Okay, electromagnets work really well because it's basically a magnet you can turn on and off by turning a current on. So how we create an electromagnet is like this. We have to have some kind of coiled wire, right? Some kind of coiled wire around a bar magnet, around some kind of bar. Okay, usually a soft iron core. When we switch the electrons on, they flow. As they flow around like this. As they flow around, they're moving. So we have moving electrons. Moving electrons are going to create a magnet, okay, which means we can pick up the nails. Once I switch it off, which is that's a switch symbol right there, okay, then once I switch it off, we're going to have the magnets fall off because the soft iron core is no longer magnetic. What we're doing is we're forcing a magnetic domain, right? So electromagnets use electrons to force a domain. Right, force a domain, or forces the domains to line up. Right, forces a domain to line up. All right. Okay. The electric current is in a straight line, right? So electrons always flow from the negative side to the positive side, and as they flow, they create a circular magnetic field. All right, so they create a circular magnetic field moving around this. So you can see that here, that as the electrons flow, they create a circular magnetic field. What someone figured out at some point in history is that what if I loop the electrons if I loop the electrons around, they actually create a magnetic field within that bar, or within that loop. So even without the bar, we use the bar basically to create magnetic power, but without the bar, we still get some kind of magnetic field looping around. The same as we would see if we had a bar magnet in there, north and south, south and north. Okay, within the coil, within the actual coil, the magnetic field is straight. So in the center, the magnetic field is very much straight, north and south, north and south. All right, we're going to get into some three-dimensional things going on here, so we have to actually use some notation here. Okay, so we're going to have what's called an arrow directed into the page and an arrow directing out of a page. If you think of this as if you're actually shooting an arrow at someone, right, like a bow and arrow, it's going to have kind of this, oh, these are good pictures, guys. It's going to have this kind of fletching on it, right? And as you go, as the arrow was shot away from you, it would look like this, right? So that's the arrow going into the page. If the arrow was shot towards you, you would see the tip of the arrow coming at you. So X's are into the page and dots are out of the page. All right, so that's just some notation that you're going to need to know. All right, so the first thing we have here is what's called the first left-hand rule for straight wires. So if you take your thumb and you wrap it around a wire, okay, take your thumb and wrap it around a wire just like this person's doing here, and your thumb is going to point in the direction of the electron flow, and it means your fingers will point in the direction of the magnetic field. So it's your left thumb of your left hand points in the direction of electron flow, fingers will circle the wire in the same direction as the magnetic field, right? Okay, so if we know like that, okay, we're going to have, I'll draw an example here. Okay, I have a wire going this way and the electrons are flowing like that. So take your thumb, right, your thumb will point up and you'll wrap around, which means the electric field on the left hand side will be going into the page. So you put little X's, and on the right hand side be coming out of the page, right? So you put little dots. Okay, and then everywhere else it flows, right? So you can kind of draw lines like this to present it, but that's kind of it. You grab the wire with your hand, thumb is the electron flow, and the fingers around is the magnetic field. All right, okay. Please note there's also this thing called conventional current. Conventional current came from the idea that they originally thought that protons moved. Okay, this has to do with protons. Okay, we know that protons don't move because they're trapped in the nucleus. If we move protons, we get a kaboom, right? So protons don't move, but it's still considered conventional current because it's the way that they thought about it for a very, very long time. All right, so if we're going to use our left hand shows electron flow, then our right hand is used for conventional current, which we're not going to see very often. Okay, so that's the first left-hand rule. Okay, first left-hand rule for straight wires. All right. Oh dear. Okay, so now we have the second, or kind of using this idea. So we go here. Okay, we have a current carrying this through it. So we have a wire producing magnetic field circling the wire. Use a hand rule to determine the direction of the electron flow in the wire. So if I look here, I have got the magnetic field is kind of going in front and then behind, right? So it's going in front and then behind, looping behind, then in front and looping behind, right? Okay, if I do that, it means my fingers would wrap around it this way, in front and then behind. So if I do use my left hand, wrap my fingers around, my left thumb will point to the right. Right, so my thumb will point to the right. Since my thumb points to the right, okay, since my thumb points to the right, it means that the electron flow is to the right. Okay. Oh, this is difficult from a distance, you guys. I'm sorry I can't show this to you better. All right, current carrying wire, electrons flowing to show. Okay, you can see there's electrons flowing up there. All right, produce a magnetic field circling the wire. Use the hand rule to determine the direction of the magnetic field circling around the wire. So the electrons are flowing up. Okay, they are going to flow around, and we grab the wire with our left hand, and our fingers will circle around this way. So the magnetic field is going to go out that way, okay, and then back over this way. Okay, so it's going to go behind and in front, but we have to use our arrows, right? Or we can also just do our X's, right? That's into the page, and the dots are out of the page. right? So it's going to go into the page where the X is and out where the dots are. Excuse me. All right. So again, we can show this method is using our dots and X's, right? Okay, a straight wire is orientated along the vertical, and a battery is attached so that the electrons flow through the wire downward to the ground. The two diagrams are given below to represent the situation. The first from the point of view of the observer on top, and the second from the point of view. So what I've got here is I've got a wire, all right? This is a wire that's flowing away from you, right? So you're almost looking at the end of the wire, and the electrons are flowing away from you. If you take your left hand and you're going to take your thumb, and your thumb's going to kind of point at the paper in this case because the electrons are flowing away from you, which means which way is your magnetic field? Well, we have our magnetic field is where our fingers go. So it's going to look something like this in this direction, right? We're going to be going in this direction as our magnetic field. Okay? Same idea with the second one here. Take our left hand, the electrons are flowing towards you, so your thumb should be pointing towards you in this case, and your fingers wrap around. So as they wrap around, you'll notice that the magnetic field goes in on this side and comes out on this side, right? So X's and dots. Again, sorry for the writing not being perfect. Alrighty. Second left-hand rule, okay, is that the left hand grasps the coils and the fingers curl around the loops in the direction of the electron flow. Okay, the thumbs point in the direction of the north pole of an imaginary bar magnet inside the coil. So think about your fingers go around in the direction of the electrons, and then your thumb is going to point in the direction of the magnetic field. Okay, so what this kind of looks like here is you have to wrap your fingers around. Okay, so if I look at this one here, I look at the electron flow, it's going this way. I notice it goes behind first. So you're going to take your left hand, okay, and you're going to wrap it as if you're grabbing the bar. So your hand should go behind that bar and around, just like the electrons are going behind and around, right? Which direction is your thumb pointing? Your thumb should be pointing to the left. If your thumb is pointing to the left, that's the direction of the magnetic field, right? So the left, so that means that this end of the magnet would be south, and this would be north. Okay, so your thumb's pointing to the left, this is south, and this is north, right? Remember, your thumb is going to point towards south in this case. All right, again, if I change it up and I look at the second one here, right, we're going to do the same thing. Okay, look at the second one here. We're going to do the same thing, and we're going to see that the electrons flow from the negative and they also go behind the bar and then come out of the front, then behind and come out of the front over and over. So you're going to wrap your fingers, they're going to go behind and come out of the front. Again, which way does your thumb point? Your thumb should be pointing to the left. Center's thumb is pointing to the left, this is south, and this is north. All right. Okay, these two rules are ones that you guys are going to need to really get down. All right, notice again for the second left-hand rule, if it's conventional current, which you'll be told if it's conventional current, you're going to use your right hand, and the same theory applies. Okay, all right, so that's where we're going to end lesson 1. You have practice problems 1 and 2. Okay, you have practice problems 1 and 2. Those should be very straightforward, and then keep going on your anticipation guide. You guys can actually finish your anticipation guide. This is going to be a long process, but we'll get through this all, and hopefully we can go from here. All right, thank you, and I'll see you guys in the next lesson.